The next talk is Colin O'Flynn, Power Analysis Attacks for Cheapskates. Thank you.
All right, thank you very much. So thanks everyone for... All right, I like it clapping before I begin. Start off on a good note. My name is Colin O'Flynn, and this presentation is about power analysis attacks for Cheapskates. So maybe you're wondering, do I want to go to this presentation and another one? So I'm going to give you a quick 60-second version of this, the next 60 minutes. Basically, with power analysis attacks, we have some sort of crypto hardware. Crypto hardware being hardware that actually has cryptography implemented in it, or even just a general microcontroller running crypto libraries. And we can look at the power that device is consuming on a very short time scale, clock by clock cycle, to figure out some information about the data that it's processing. Once we figure out that, we can actually break the encryption, that is, figure out what the secret key was or some other secret that we're not supposed to know. Normally, and people have known about this for a long time, 10 plus years, normally they're using pretty good oscilloscopes like this. This is in my lab at Dalhousie University, where I come from. And they have some crypto hardware and stuff like that as well. And it's a pretty expensive setup, you know, at least a few $1,000s, maybe more, and then you have to write some software and whatnot. So I've developed some open source hardware, open source software for doing this. So this here, you can see some PCBs, you can see an assembled device there. And this hardware, as I said, is totally open source. You can even build it using odds and ends you might have around if you're really good with electronics. You don't necessarily have to stick to the plan. The point is I'm trying to make it available to people who are interested in this field but don't want to spend 10 grand, 100 grand on a scope. All right, so that's the intro. Now about me quickly. I come from Halifax, Nova Scotia, so this is maybe the famous Peggy's Cove in Nova Scotia. If you go, it's quite nice. We're having a heat wave there at the moment, and I believe it's 31 Celsius, which I don't know what that is in Fahrenheit, but it's very hot for me here by comparison. This is Halifax that I come from, so here's one of a very rare occurrence of looking at some power over our city. We get maybe one storm a year like that. And my background, so you can say, well, is this something I want to do? I like to introduce where I come from so you can sort of understand if this is your sort of field, this might be interesting to you. So I come from originally doing embedded stuff. I did a lot of work with the AVR compiler, which is used by Arduino and stuff like that. I've done some writing for Circuit Teller magazine, and I'll have a column coming out every 2 months in October. And as well, I've done some various hardware design and some other open source tools in the Zigbee field, and run some various Kickstarters doing some hardware and software design. So my background is almost entirely embedded hardware, not necessarily security. And this is the approach I'm taking with all this work. And I think you'll find it makes it fairly available because I want to make it easy, and maybe I didn't have the security background some of you would have to start with. So what's the motivation for this presentation now? The motivation here is the number one thing is not for the Leap Hacksaw. So all these tools are not something you're going to take and say, oh great, I'm going to break a system now and expose them on the internet. It's absolutely not about that. It's about learning solely. You're going to have to learn how these attacks work. You're going to have to learn the theory behind them. You're going to have to know about hardware design, about software design, programming both the device, the embedded target, and programming the computer itself with the algorithm you want. And of course, you're going to get frustrated, run into many bugs with the tools, and you're going to have to fix them yourself. So that's all the disclaimers I give you, and now I'll start introducing what is the side channel. So maybe you already know what power analysis is, maybe you don't. For those that don't, I'm going to explain how this whole thing works. So we have a crypto device, we have, you know, a smart card, we have a embedded device with a bootloader, we have something like that. We have a channel, and we can send it a request. We can say, please encrypt this, and it'll respond and say, okay. It might not be exactly like that, but it might be you send it a encrypted bootloader and it decrypts it. The point is we have a way to cause the device to run an encryption operation. And you can do that all day. You can run encryption on it, and you're not going to figure out what the secret is inside it. But it has other channels. It has other communication methods. It didn't intend to broadcast, but it is telling you something. It's telling you something about the secret inside it. So what we use is the power channel. How does this work? Imagine you had hardware. I call it the Crypto Pro 9000, the latest in 4-bit cryptography. Inside it like any digital device ever, you have some stuff connected by a data bus. So here I have a arithmetic logic unit and a RAM, and there's this data bus, these 4 wires in between them. This could be registers, this could be anything inside a CPU. Those data bus lines just look something like this. So we have a FET, which is an electronic switch at the VCC rail, the positive rail, and at the ground rail. If you want to switch one of those data lines, so there would be 4 of them in this case, to high or low, you connect one of these FETs to the appropriate bus, so ground or positive. This bus is effectively just a long wire, and it really looks something like a capacitor to the system. Now from high school physics, you might know that to change the voltage on a capacitor, to change the state, you're moving electrons. You're physically doing something. Physically doing something takes energy to do this. So if you change it from a 0 to a 1, you're taking energy, power from this positive rail here, it's going onto the capacitor. To change it from a 1 to a 0, you're taking energy from this negative rail to change the state of the capacitor. So it physically takes power to do that. Importantly, all of those data lines are switching at the same instance in time. They're switching relative to a clock. So we have a clock on the digital system, and you have the 2 data lines. When that first clock edge happens here, these 2 data lines switch. So on this side, first clock edge, 2 data lines switch, and there's a big positive spike. There's a big positive spike because 2 of the data lines are switching. At the next positive clock edge, only one of the data lines switching, and it's going from positive to negative, so we see a bit of a negative spike. So what we're learning about is on each clock edge, we're saying, well, those data lines, 2 of them switch from 0 to 1, or 1 switched from 1 to 0. We don't know which one, but we know how many changed. So we call this the Hamming distance. We're learning the Hamming distance of data that was on the bus before and is on the bus now. This reality exists for some hardware implementations of AES and some hardware chips. The other reality that is more often the case for embedded microcontrollers is what we call the Hamming weight system. So despite what security people always seem to think, these embedded engineers that make these systems are not idiots. They're trying to optimize a lot of stuff. One of them is the power consumption. So if you have all of the data lines switching from 1 to 0, this is the worst case situation. You have a big power spike there. That means most power consumption. You're limiting your clock speed. So instead what they do is they always switch the data lines to a pre-charged state, which is effectively this intermediate middle state here in dashed lines. This pre-charged state is halfway between the 1 and the 0. The point being that when you want to switch the data lines to the 1 state, you no longer go from 0 to 1 potentially, you always go halfway to 1. So it's half the required power. So your worst case scenario is now much better than when you're switching all the lines from completely to 0 to completely to 1. What this means to us, people who are interested in analyzing the systems, is that we can look at the power on each clock edge and say, well, this clock edge, 2 data lines switched from the pre-charged state to 1. On this clock edge here, 1 data line switched from the pre-charged state to 1. And the power, I'm looking only at the positive rail, so I'm only looking at positive transitions. On this clock edge here, no data line switched, so it was all 0. So we're actually learning not the difference, but on each clock cycle, we're learning the amount of 1s that were put onto the data bus, or the Hamming weight of that data. So now, on every single clock edge, we're learning the Hamming weight of the data. So this is the information we'll use to break the cryptography itself. With any sort of crypto algorithm, we have A and B. We have the input and the output, plaintext, ciphertext, or ciphertext, plaintext. You could play with them all day, and you're not going to break the cryptography, but there's some intermediate state, which I've shown C here, where you could break the cryptography. You could learn something about this intermediate state. The algorithm is not as secure. So if you want to look for a specific example, let's take AES 128. So AES 128 does this in a number of rounds. So we have the input up at the top. It does a bunch of stuff. You don't really care what. And it does this 10 more times. So you can start to see it repeating there 1 time. And there will be a bunch more rounds of this. So if we look at just one of these input bytes, and we magnify it a little here, we can see we have 1 byte of input on the P there. Maybe it's a little off screen. But there's 1 byte of input. oh, there it is, sorry. 1 byte of input plain text and 1 byte of key. We take the plain text and we take the key, we XOR them together, you put them through a substitution box, just a lookup table, and it goes on to the rest of the algorithm. We do this 16 more times, so you can see this same thing is just repeated for each of the bytes. So we have 16 bytes in the key, 16 bytes in the input. So what we're going to do is, rather than trying to attack based on the input and the final output, is we're going to say, well, if we could figure out this state right here, this intermediate state, I could trivially find the key because I know the output of the S box, I can inverse that. I know the input plain text, assume I'm sending it some data or I can see the plain text. And from that, I can then figure out what the key is. So that seems good, but there's still a little bit of a disconnect here because I've only shown you how to find the weight of the data, not the data, and we need the actual data for this to work. So again, let's take our 4-bit chip. And let's say I'm just trying to figure out something simpler. I'm trying to figure out the plain text I put in here. There's a key that I don't know, and the output of this XOR operation is unavailable to me. So this is effectively what you have in real life. We use what's called a correlation analysis to do this. So to do this, you put in a whole bunch of effectively random data at the plain text here. So I'm just going to put a bunch of data I make up in. I can record what that data is. I know what the data is. And then I'm also going to record the power as the system is doing this. The result is that I've recorded the power while it's doing something with data I know. I'm now going to take what I know, so I know the input plain text here, and I'm going to guess what the key is. So in this case, there's a 4-bit key. There's 16 possibilities for that key. And I'm going to make a table like this for each one of the guesses. So for each one of the guesses, I'm going to say, well, I know I put in a 4 as the input. The key could be 2. It could not be 2. I don't know. If it was 2, the hypothetical result would be 6. That hypothetical result would have a hypothetical Hamming weight of 2. And I'm going to do that for each of the input plain texts that I know I put into the system. And now all I have to do is correlate between the hypothetical Hamming weight here and what I actually measured the power of the system being. Because if this was correct, if my hypothetical key was correct, I expect to see a relationship, a correlation between the hypothetical Hamming weight there and the measured power, which is related to the measured Hamming, or the actual Hamming weight. For the rest of them, so for the wrong key guesses, I won't have this correlation and it'll just fade away. So then you just pick the one with the highest correlation and you repeat this for each of the bytes. So now with the real system, with AES-128, we don't have a 4-bit key, we only have 8 bits to deal with. Again, only 256 guesses, not a big deal. One thing you might notice is that the XOR wasn't a perfect example for this because when one of these bits changes in the hypothetical key, you only get a little bit of difference, 1 bit of difference in the hypothetical result, and again, a small difference for the Hamming weight. We'll actually attack nonlinear functions like the S-box or mixed calls, which gives us a nice nonlinear function so that when you change 1 bit in the guess, you'll get totally different hypothetical results. So if you wanted the algorithm written out, so to speak, it would look like this: correlation power analysis. Input many plain texts and measure the power. And then for each of these bytes, do 2 and 3. So 2 is you guess the keys. There's 256 possibilities for that byte of the key. Based on the plain text you know you put in, you calculate the S-box output. You use a power model, which was basically that Hamming weight thing I talked about, to predict, well, if that was the output of the S-box, this is what the power would look like. And then finally, I measure the correlation between the model and the measured for all those traces I put in. One of these is going to give us the highest correlation, and that's probably the correct key. You might notice this sounds familiar if you're sort of an engineer type. This is actually what's known as matched filtering. It was effectively rediscovered in the field of side channel attacks. Matched filtering is exactly this, and it's used in radio receivers to decode what signal did I receive. And this has been known for many years, 20, 30 years, I think. So the point I'm trying to make is a lot of this isn't really advanced. The actual theory behind it is quite simple and quite straightforward. So there's one part I sort of glossed over when it comes to actually doing this. How did you measure the power? I just said you measured the power of magic. So if we have a device like that with the fancy lines coming off it, we can use an electronic component called a resistor, and you just insert the resistor into the power line. Resistors very conveniently follow what's known as Ohm's law, which says the voltage you measure across them is going to be related to the current through it, aka the power times the resistance. So we can measure the voltage with something like here I have a voltmeter. In reality, you'd use an oscilloscope to get this in very discrete time periods. Alternatively, if you don't want to do that, you can use your knowledge of Ampere's law to say that, well, a current in a wire creates a magnetic field. Thus, if I'm changing the current going through this wire, I can just use a magnetic field probe and detect what the current is. And then you don't need to physically change anything. You can just put a device down, have your probe, and it all works. So that's the theory behind it. What have I sort of done? That part has been well known for many years. So what this presentation is sort of introducing is what I call Chip Whisperer, which is a collection of open source tools and hardware, as well as stuff like a wiki and a mailing list, for helping you get into this. And everything that I'm showing you is in that repository, absolutely everything. Even, I don't know if the slides are there, but they're posted on the website. So it's completely open. And unlike people who say this and say, oh, well, I'm going to be putting, oh, I don't have it here. I'm going to be putting this in shortly. You can see, I've been committing to this. I was doing a bunch of work fixing bugs when I was in the airport coming here. So, thank you. It all worked, actually, too. It didn't work until about 26 hours ago, properly. So there's two main tools. One of them captures the data, so it's writing the plain text. I said, you send a bunch of data to it while recording the power. So that's the first tool. The second tool applies that attack I just described. So you can use whatever you want. You don't have to use these tools. You can use the capture tool and then use MATLAB, or you could use your own scope and then use the analyzer tool. It's not some special suite. There just happens to be two. It's all written in Python because Python is disgustingly easy to make good-looking stuff. And it's not the highest speed for sure, but it's not designed to be the end-all and be-all. There are commercial tools that do this that are very expensive. I'm aiming to make something that's great for open source for people who want to learn about this. So very briefly, this is what the capture tool looks like. So we have the trace we're capturing here, and we have a bunch of settings. I'll show you it running after this. The analysis tool will look something like this. So before, how I said, we're doing this for each byte. We're going along and saying, well, byte 0, byte 1, byte 2. We're doing this correlation analysis. So in red, this is the correct key byte, and you can see how we get a bunch of very high matches at some point in time. At this point in time, this is when that step, that S box that I was guessing the system was doing, that's when it's actually doing it. So the other part of this tools, or this whole correlation analysis, is you don't have to know exactly when that encryption or that S box occurred. You can figure it out from the traces. All right, so how do we get the waveforms, and how do we do that cheaply, the cheapskate part? So I told you before, this is sort of a normal type setup. We have a fancy oscilloscope, we have a board, we have some probes and stuff, and they're pretty expensive. You can look at literature, you can look at other people who've published these type of things and say, how much did it cost them to set up their lab? And I just did a quick survey a while back, or not that long ago, and said what was the cost of the scopes they used in their paper used to buy today, not the new cost, because that's not fair. And it works out, it varies between $1,000 maybe to $20,000 plus, and it depends on the type of hardware they're attacking. Why do they have such fancy oscilloscopes, you might ask? They have it because we end up with something like this. What I'm showing you here on the y-axis is the partial guessing entropy, which is to say the final result. Did I get the right answer or not? When the entropy goes to 0, that means I know with certainty this was the correct answer. When the entropy is high, I need to do a lot of guessing to figure out the right answer still. So an entropy of 0 is good. On the bottom, we have number of traces, which is when I said, I'm going to put in a bunch of plain text. How many plain text did it take? How many power traces did I have to record? If it takes me 10 million traces, that's not really realistic. If it takes me 2, well, that's really good because I can actually attack a system. So with an oscilloscope sampling at 500 megasamples per second, you can see this point where it reaches 0 is a little over 20 samples, so pretty reasonable. And the target I'm attacking, by the way, is a embedded microcontroller running at 7.37 megahertz. doing software AES. So a very, very simple target. This is nothing complicated at all. As you decrease the sample rate, so you get a cheaper scope, this line increases. So when we go to 100 megasamples per second, it gets a little worse. When we go to 50, a little worse than that. And at some point here, 25, you can see this line is decreasing very slowly. So we've basically lost the ability to do the attack. Why this happens is that the oscilloscopes run on a sample clock. When I say it's doing 100 megasamples per second, so on the top we have the sample clock here, this clock is running at 100 megahertz, and it's saying, okay, every 1 over 100 megahertz, I take a sample of the power the device is using. The device clock is also running at some other frequency, so in my case 7.37 megahertz, so here's the device clock. There's no relationship between those. So on the edge of the device clock, that's when the operation occurred that I want to measure the power of, but it doesn't get sampled to some time later when the oscilloscope takes the next sample. The next time that happens, and you want this to be very repeatable to line up all your power traces, the device on this edge here, it does its thing, and the scope takes its sample when its next scheduled time occurs. Regardless, even though I'm triggering the scope perfectly, it just cannot sample until that next rising edge of the sample clock. And there's this jitter here, basically, there's this difference between the two. And that will change every time. If you sample very quickly, obviously, if this sample clock's going up and down very fast, that spacing decreases, this problem's not a big problem anymore. So this is why high sample rates are very convenient, is they reduce this trigger jitter and you get better results. As an alternative, rather than just cranking up the sample rate, you can take a smarter approach, which is to say, well, it's a digital system, I probably have a clock. I can just use the clock and sample on the clock. So if I insert into this graph that line there, it's sampling at 7.37 megasamples, so about 70 times slower than that 500 megasample line here. And all of a sudden, it's fairly successful. And you see this. For this, maybe it doesn't look so bad because, well, you can buy a 500 megasample per second oscilloscope. But if you're attacking AES hardware running at 24 megahertz, even 100 megahertz, you suddenly need a 2, 3, 4, 8 gigahertz per second, 8 gigasamples per second oscilloscope, and that gets very, very pricey. Whereas if you only need to sample at 100 megahertz, that's trivial to do with, a few $100s worth of hardware. The one sort of small change when you're doing this with its sample clock is you need to be concerned about phase shift. So we can see in red there's some sample points, so I could say, well, if I could sample here, that's really good. It may be that because of delays in the system, I actually sample at the 0 crossings and I really don't get any information, so this bottom one. So you need to be able to control when the sample occurred relative to the device clock. You also may take the device clock and multiply it by something. Here I'm multiplying it by 4, so this is what I tend to do a lot when I'm doing these examples, is I'll take the clock, multiply it by 4, and then use that to sample the power. Part of the reason for doing this is it gives you a nicer looking waveform. You don't necessarily need it, but it's easier to set up. So as an example of that in A here, this is a AES hardware running at 24 megahertz, doing the same operation 10 times. The top one is sampled with a regular oscilloscope, 100 megasamples per second. The bottom one is sampled synchronously at 96 megasamples per second, generated by 24 times 4 equals 96. So in B, you can't even see that there's 10 overlapping samples. They're exactly repeatable. In A, there's no chance that this is going to work to recover any information. So if you want to use a regular scope, you don't have to use the hardware I'm showing you or build your own. You may have a scope and you say, I want to use that. You can actually do a hack to do this process in reverse. So rather than synchronizing the scope to the sample rate, synchronize the device to the scope. Some scopes will tell you the time between that trigger and the first sample, and you can do some digital processing. You have lost information due to that jitter. You cannot completely recover it. And you can also sample at the highest possible rate your scope supports, because you want to reduce that initial time as much as possible and then downsample, because once it's started to sample, you don't necessarily need it so fast. You just need that initial delay to be as small as possible. To do it synchronously, a few oscilloscopes let you do synchronous. It's fairly rare. So I designed this hardware I call OpenADC. So it's an open source ADC board, and it basically has everything I talked about. So ability to multiply clock, do phase shift, store memory, adds in amplifiers in the front end and stuff like that. The most basic way of getting it is you can build the board here and mount it on this super cheap development board that's $90. So, you know, it's $150 type solution if you build everything yourself. It was sort of limited though. It only had a serial interface, so that's kind of boring. Instead, this is the latest hardware I've designed that I'll show you here. So there's these boards, all the designs are here. And you can use this with an FPGA and either mount this ADC board or build an ADC board on it. When you combine everything, you get a complete system for doing this side channel analysis. And eventually I'm trying to build and sell them as a complete package, but this is the exact same thing as this. It's just one's pre-built, one requires you to do a bunch of soldering. Or you can use, if you do FPGA development already, you may have a suitable board. Typically any Spartan 6 board, because that's what I'm using, can easily be modified. So what would your first attack look like? And this is what I'll demonstrate after. You might say, well, I've seen demos with this stuff and they attack a smart card. That's cool. Smart cards are great to attack. The problem is they'll frequently use these cards, these AT mega cards or fun cards. And these cards are cheats because they are a regular microcontroller that happens to be in a smart card form factor. Nothing about this is special. In fact, you're doing a disservice by using these AT mega cards because they use an old microcontroller that has much larger power signatures because it's a larger geometry. You can buy a recent microcontroller and just program it yourself and you save yourself that hassle. So this might look something like this if you wanted to get into it. You have a microcontroller on a breadboard and you have some support circuitry around it, basically the USB to serial converter and some power supply filtering. I also have the ADC board I talked to you about, so this is the super cheap example here, all hooked up. So there's a closer view of the microcontroller. So this resistor here is the shunt, so I'm measuring the power across that to see what the device is doing. And in a similar way, you could build this onto a physical board if you wanted a platform. Or something newer and better that I have here is what I call the multi-target victim. So the multi-target victim has a board designed with this microcontroller on it, that same one you just saw. It also adds in some other options. This X Mega device is a hardware AES engine, and there's the familiar smart card type interface, so you can work with smart cards once the software supports that. So, step-by-step guide, very briefly. You'd first have to figure out what you want and buy it. You could just use your existing tools and modify, if you have a scope that works, modify the tools to work with that. Or you could build everything I've showed you here. So either get your own PCBs made, make your own, order some pre-made ones from this other guy that's selling them for me, and get a bunch of parts from DigiKey. Assembling them is like assembling any electronics device, basically 2 steps. First, you would carefully mount the small resistors that you might be able to barely see mounted on the board there, and then you would just build everything else and you're done. So that is the 2 steps, and you can have your own chip whisperer. You then test it. So you'd confirm maybe the target's working, so I send it a key. You can say maybe I set this key. So this is a super simple protocol I'm using for testing. I send the key, I send the plain text, it returns in green with response, so that's working. You need to characterize it, which is to say, do I have too noisy of a system or not? If you have too noisy of a system, you'll need to take steps to mitigate that. So here what I've done is I actually connect this probe just to the power supply of the system. So the positive rail basically, and I'm then going to see how much noise is on that positive rail. If there's too much, it won't work very well. If there is too much, like there was in that previous case, I'll add filtering components to bring it down. And finally, we'd insert the shunt, so we have a resistor here, and then it measures to your oscilloscope or whatever else you're using. And then you could basically confirm that you're getting reliable triggers. So I'm using a persistence mode, which just overwrites captures, and you would adjust whatever you need to adjust on the oscilloscope you're using, be it the gain, the phase, the type of trigger, to get your reliable signal. You could then acquire a bunch of traces and run the power analysis. So we're going to see if this works still. So what I have up here is this tool I just talked about. So if I take this off, I'll give you a bit of a view of it. So this is that chip whisperer, those boards I showed you. I have the target connected here, and I've taken the back panel off so you can see there are those 3 boards on the inside. So we'll put this here. That may fall over, but that's fine because I'll switch now to the software. So the software looks something like this. So I've already set it up to save time, and we can see we're getting a number of power traces every time I press 1. So I've already configured the gain and the phase to get my reliable signal. I would select how many traces I want, say 100, and just hit this button, and you can see at the bottom it's sort of saying trace 37 done, it's counting up. And if I switch very quickly to the camera here, you might see some blinking lights, but I think it's already done capturing. So it doesn't take long. It's just captured 100 power traces. So I'd save this. You can see I did a few test ones here.
Is that a synchronized capture?
Yep, so this is using the synchronize, so it's taking the clock to get this. So that's why it looks so good.
Colin, do you have an oscilloscope, or is OpenADC doing just...
OpenADC is everything, so it's...
Right to the machine.
Huh?
Dumping it right to the machine.
Yeah, it does everything on there. So that whole hardware is like a few $100s worth. So then the second part is you'd open the analyzer program, open project, and you can enable the traces. So that's the power traces I just acquired. And there's this big attack button on the other side, and you just hit that. And this does the power analysis. So this part takes a while, especially because it's doing stuff in Python and math and whatnot, which you don't want to do, but I'll let that go while I talk about the next stuff. And we'll come back once it's finished plotting. So maybe you do want to attack real smart cards. What can you do? You would get something like a smart card reader, and you can just insert a shunt. So I've just soldered a small resistor there and pulled out some of the clock and sync and so forth. And you end up with this, like that. And then you can connect it up. So here I'm using the OpenADC on the LX9. You could connect it to this other device I have. They're the exact same thing effectively. One's just a little nicer. You could also build cheaper readers if you want. So all this detail schematics are either in the repository or white paper or somewhere in between. There's a very cheap, like $10 smart card reader. And you can also do with the multi-target board what I call an in-the-middle attack. So we have this fake smart card looking PCB. This PCB is plugged into your reader. The other side goes around to the multi-target capture board where you have a smart card inserted into it. And in this way, the signals are going through to the reader while you measure the power, while also monitoring all the signals. And you can do insertions in the data line if you want, or glitches. So let's see if the demo is done running yet. All right, so unfortunately, this screen resolution is so low. We can see at the top here, so this is ranking for each key byte, what it thinks the most likely, what it thinks the most likely byte is. So if we go along, we can see 2B, 7E, 15, 16, 28, AE, and so forth. And we can see that these first few bytes are actually what the known key is. So the known key is what I told it is here. And it perfectly matches. So it goes 2B, 7E, 15, 16, 28. And at some point it's wrong. So AE is correct. And then it starts to lose it. This is because for speed, I only captured a shorter range than I really needed of the point. So I can show you afterwards a demo of the whole thing working. All right, so one thing I mentioned briefly is you could use magnetic field probes to do this instead of the physical shunt. How would you do that? Well, you'll just buy a probe set. They're kind of expensive though. Like this set here is $2,500, $2,000 from another company. This company makes one that's a little cheaper, a few $100s each. And here's probably the cheapest full set, $1,600. Either way though, it's a moderate amount of money, definitely not the cheapskate way. But what you can do instead is spend $3 on this cable, and you can make a little loop here, and you cut a slot in it, and you have a pretty good magnetic field probe. You probably want to wrap something around it so you don't short out whatever you connect it to, or you could use Plasti Dip if you wanted something nicer. And all the theory from that comes from not something I made up, but this reference here, probing the magnetic field probe. This guy has actually done research into how well the different types perform, and there's even someone who has a thesis on using your own probes for side channel analysis. So the point is, you don't have to buy one, you can very easily make one that's just as good as what you buy. The other thing, when you buy the probe, what you'll need is a preamplifier. So the preamplifier is used to amplify the signal from the probe to make it work with the oscilloscope. And again, when you look back at the price of the probe, they often were saying you can buy one. Let's see, here's one. If you want to buy the preamplifier, it's an extra $300 in the set, or sometimes they sell them for more. And again, you don't need that. You can just buy a regular low noise amplifier for $90. If that's too much for you, you can buy a amplifier chip for 60 cents. And this chip works almost as well as those preamplifiers that officially are sold. So you need a few components around the chip, obviously, and you end up with something like this that you can build on. Here I've built it on, perf board type stuff, so not even proper RF design. And that particular one I showed you, let me go to the figures first, it's giving you about 20 dB gain, which is effectively 100 times from 80 to 400 megahertz. If you're using it in a lower range, if you're attacking a slower device, you get a little less gain, so 0.1 to 10 megahertz, we get about 40 times gain. And there's also a board design for this that looks a lot nicer than the one I just showed you, and it's easier to make. So there's an example of using it to probe a device. So what else might you need? Well, there's also a differential probe that can be very useful. So what a differential probe is it answers one of the questions I brought up a long time ago, was how do we deal with this noise? I said you've got to filter it and fix it, or else it's going to ruin you. Not necessarily true. Many papers you'll see use differential probes. So here's a paper on someone who did some work on the X Mega, and in their lab setup you can see this differential probe. Why we use it is, we know from before Ohm's law, voltage equals current times resistance. If we were trying to measure something like, this 0.2 milliamp signature, so I'm trying to capture a tiny variation in the power, across that 75 ohm resistor, it's going to mean I'm trying to measure about 15 millivolts. If we have a lot of noise in the system, this might be here, 20, 50, 100 millivolts peak to peak of noise, it's going to obliterate that signal, and we're not going to be able to recover the signal. So instead what we use is what's called a differential probe. All this does is, you can see how there's a probe here and it's connected on each side of the resistor, that shunt I'm measuring with. The noise in the system tends to be coupled onto both sides of that resistor. So the noise coming through this line will more or less be coupled evenly to both sides. There's a tiny bit of variation, but we don't care. Now, this probe is only measuring the difference between the two sides of the resistor. So the noise that's common is irrelevant to you and to the measurement then. So this is a really easy way to sort of obliterate that noise problem. And that probe in this paper, if you say, I'm going to recreate this guy's experiment, okay, I happen to have that scope, say, because it's also very expensive. I need to buy that probe. Well, it's, how much is it here? 4,500. This is Canadian pricing, so you have to convert to whatever the exchange is, like $20 American or something. If you want a slightly crappier probe, because you say, well, that one's very expensive, I don't need that. Let's get a 200 megahertz probe. It's still, $1,500 about. Even if you go used, it's still expensive. The probes are high quality instruments, and they do tend to be very expensive. But you can build something for what we're doing that works well enough, has pretty good high frequency response for about $5 using this, or with a $5 chip, plus a few other parts. And this chip will work more than well enough, and there's a nicer version now with PCBs and whatnot. So this shows you the design of the chip whisperer in the background. There's this differential probe, and you just plug that onto the board. So at this point you might say, well, this has been interesting, but way back at the beginning you claimed this was going to work on real systems. Everything you've showed me is that fake target and this breadboard. Like, no one's attacking a breadboard. This isn't a real system. And there's a few things when you do real systems that are slightly different. So number one is I always assume you have the clock. This is pretty safe to assume for a lot of digital systems. Not all, because some systems may have internal oscillators inside the chip stopping you from tapping it. You can use a clock recovery system. So this is, I won't go into detail, but almost exactly like it's done in communications electronics. It's been known, again, 20, 30 plus years, this sort of idea. You can use that to recover the clock and then attack the system, and this works quite well, even if the clock changes during operation. You also need to be able to tell the device, hey, do an encryption now because I want to monitor you. Well, you don't tell the second part, but the first part. So in real life, you can often do this. Smart cards will frequently have authentication commands or similar. So it's simply a command saying, I want to prove you have access to a key. So I'm going to send you data, you encrypt it, and send me back the ciphertext. This is encryption on demand, so that's perfect. You're done. You might have some sort of encrypted communication, a Zigbee type device, 802.15.4. If you send it an encrypted block, it's going to take it, it's going to decrypt it, and then reject it. But you're forcing it to now do the decryption with some sort of input you control, so you're done. You might have an encrypted bootloader that you wish to figure out the key to, for example. Again, you can use the same sort of idea. You send it an encrypted device firmware file. You know what that file looks like. It's going to try to decrypt it. So you can say, well, while I'm monitoring it, I know exactly what it's going to be attempting to decrypt. So, for example, this is pulled from an app note directly, and they're telling you, here's how you make an encrypted bootloader. You take up your file, you chunk it into frames. Each frame has a bunch of encryption plus a CRC for detecting errors. And then you just send it to the device. The device, if it receives a valid frame, valid mean it has a CRC, there was no transmission errors, it will then say, all right, let's decrypt it, and then it checks the signature. But all you care about is that you can force it to decrypt something. So again, you're done, you win. The final thing is that I'm right now using the device itself. When I say run this encryption, it says, okay, I'm going to run the encryption. It sets an IO pin high, and this is how I know right now I should measure the power. What you need to do instead is to monitor the I/O lines of the device, for example, and say, well, I know when I send it some byte, which is some binary pattern, then it's going to run the encryption, or maybe then it runs it after so many clock cycles. So there actually is support for this in the Chip Whisperer hardware. It's only loosely tested, which is to say you can say, wait until some bit pattern occurs, wait until I send the encryption command, or the guy sends back okay, and at that stage, do the recording. The other thing you might run into is how do you know what sort of library is running on it. So this is a whole other aspect of this you can use is sort of fingerprinting. So here I've taken that AVR micro and I've loaded 3 different sort of AES implementations you may find in the wild. 2 of them are from this AVR crypto lib that's quite nice and quite well used. So there's 2 different types, assembly AES and C AES, as well as I've just taken an implementation that's what I call straightforward AES, which is if you looked on Wikipedia, what is the AES algorithm, and wrote that in C, that's what you'd end up with. So they all look slightly different, but they will all break using the exact same attacks. So before I'll try to do one more demo here after. What does it all mean? So for the high level, if you're a manager, I don't really know because it's all technical to me. If you're an engineer, good standard practice does help this issue already. So if you use the same key in all your devices for the bootloader, you probably know that's bad. The problem is that a lot of people don't want to use good practice because they say, well, that's a hassle. I'm not going to have different devices with different keys in their bootloader and then different firmware files. So maybe this is a good way to point to say, well, here's a reason we should do it because here's an easy way people could be breaking our systems. And so you can use this to point out why we should use good standard practice. You can also protect against side channel analysis. So there's hardware and software things you can do that make this analysis much more difficult. And it's sort of beyond this presentation. If you're what I call the ad hoc researcher, the basic principles of everything are straightforward. So I've introduced them all to you now. The hardware itself does not have to be expensive. So you don't need that fancy oscilloscope that everyone's using. You can do it with the hardware that I've packed in my carry-on here and built myself. And everything here is about learning. So don't expect to just build this or buy this and exactly do this and say, all right, I'm a master now. I'm going to charge people $10,000 and do side channel analysis. Everything is about learning. All the tools even are written to be open and extensible, not necessarily the highest speed. So let's say you do want to get into this. Where to? The first thing is there's basically 2 books I recommend. The first one is specific to power analysis attacks. So this one, Power Analysis Attacks, Revealing the Secrets of Smart Cards. And it goes over in lots of detail different attacks, countermeasures as well. The second one is if you've always used cryptography but never actually, say, implemented AES yourself, this Understanding Cryptography book is very, very useful reference for that. Read some stuff. So there is a white paper that goes with this. There's updates to the white paper and slides compared to the ones that's on the CD or posted at newae.com/BlackHat. There's the original paper that introduced this stuff by Paul Kosher, and you can read that. It's quite interesting. As well as there's 2 conferences, CHES and COSAID. And look for the proceedings there, and you can often look when people broke real systems, how did they do it? And you can use that as a sort of template for how you can look into breaking real systems yourself. If you don't have access to these because they're behind paywalls, as a hint, most local universities will have access to all these stuff, so you can use their computers. The obvious thing is to play around, so to build some sort of hardware yourself, build or buy the hardware, and you can also join the mailing list for discussion. There's also going to be a conference on this whole stuff. I mentioned it called CHES, so it's happening this year, August 20th, in Santa Barbara, so next month sometime, and there will be a 3-hour tutorial on using this hardware at that conference as well. So this is sort of the question slide, but I'm also going to do some other demos here, so if you have questions, you can ask them now and I'll stage that in with the demo time.
I apologize, it's a very basic question, but I didn't understand from the beginning of the presentation. How are you able to identify the bytes to key sequentially? Is it because they occur on sequential clock cycles?
So the question is how do I identify?
One versus 2?
Yeah, so how you do this is that go back here. And this is also a good point because when I've been doing this, it's sort of been, so this slide, making sense? Actually, I'll go to this one here. I've initially said software AES when you do byte 1, byte 2, byte 3, byte 4, byte 5, etc. If you're doing this in hardware, it's not even that nice because they might be doing a bunch of these at once. So you could potentially even have 16 bytes done at once. So you have a 128-bit data line that's doing this all. So how do you figure out what's what, basically, right? And the answer is that you don't care what everything else is, because when you do this correlation analysis, each of these input plaintext is different to each of the bytes. So when I put the data in, I put in 16 different bytes and just 16 random bytes, basically. When you do the correlation, the only thing that will correlate is the plaintext I know I put in and the actual key the system is using. When I have these in the algorithm and it generates some hypothetical value that I'm trying to say was the hypothetical value put on the data bus 2, the only time this will work is if this hypothetical value agrees with the actual value. And you have to do this with a whole bunch of traces specifically because you don't know when the encryption exactly happened. And why I have so many traces, here I have 7. In real life, I was showing 50, it might be thousands, is over time, everything else becomes noise. Everything else just becomes white noise and effectively goes to 0. When you're looking at the correlation, but the data you care about, even though it may only be 8 bits out of 128, creates this huge spike. So when we see, go to one of these slides, when we see this huge spike here is the correlation of the device working with the data I think it's working with, I'm guessing it's working with. At this point, I'm saying my guess is correct. It is in fact working with the data I think it's working with. Everywhere else, it's not. So it's either dealing with other bytes, could be just doing other operations completely. I don't.
Even if it's processing multiple bytes simultaneously?
Yeah, so even if you do hardware AES and you do 128 bits at once, this works fine. So in particular, this, where is it? So this slide here, I didn't actually talk about this. This is talking about against a hardware AES implementation. The hardware AES is running at 24 megahertz, and it takes 10 clock cycles to do a full AES, which means it's doing all 128 bits at once on every clock cycle. It takes more traces, so here it's taking 3,000 traces, and there's a different metric plotted here. This is the success rate. So I'm saying if I measure the power 3,000 times, 80% of the time I can recover the exact correct key in this hardware implementation, even though it's doing everything at once. So it does in the end work out. Make sense? Other questions? Yep.
This might be a basic one because I'm not very familiar with crypto, but you would talk about since we know how the S-box stuff is calculated, the sort of intermediate value, how do we know that when we're capturing traces of power, that's what we're looking at, not something further on?
So this is somewhat related here. The answer is that we don't care, actually. When we do this, let me just look. So when we do this, what we're trying to say is, was my guess that, where is it? Was my guess here correct? So was, that there. You're saying that how do we know this wasn't something that was occurring later on? How we know that is that I know what the input is. I know the plain text input. I don't know the key. I'm just going to guess the key. And I'm going to compare every point I measure. I'm actually going to compare this hypothetical guess that I'm doing this correlation to. So I'm going to say, was it 0.0? If there's no correlation, no. Was it 0.1? Was it 0.2? Was it 0.3? Was it 0.4? Etc. So when we have this plot here, what I'm actually showing is that here it is guessing that, oh, it did the encryption here, it did the encryption here, 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 here. It's not until somewhere over here, 425, whatever. At that point, it was doing the encryption. So it was working with the data we're guessing it's working with. We didn't know. And that's when you see it. So you don't know when it was doing the S-box. You have no idea, right? I'm just triggering this based on, I send it, do encryption. It does a bunch of stuff, receiving data, subroutines, until it gets to the point. So that's the thing. You just have to be able to record around where it's doing the encryption, and you can figure out where it did it. So.
And then once you know that, you shift everything, and you just delay the capture.
So yeah, at this point, I don't right now. I don't know. The hardware works. Until recently, you couldn't do that with the hardware. I added that, but I haven't tested it well enough to do it live. So yeah, at this point, you could say, well, I'm going to save time, and you literally only need one sample. You could do this. If you could sample the right point, you don't need, you just need like a sample and hold system. You don't even need an ADC. But because you don't know the point, I just do all of them. And they occur at different times. So if I go along to different bytes here, so let me, so the Python, it's redrawing, which takes forever. So if you go along to different points, you can maybe see at the very bottom here, this byte was occurring around 1500. This other byte, when it eventually comes up, yeah, it's very slow to redraw. But this other byte, for example, probably occurred earlier on, because maybe it was doing the first byte and then that one. So you end up capturing when the total, the window of all bytes is. So it may be pretty big. Other questions? I saw a hand. Maybe, I think you were.
When you're doing multiple traces, you're saying you're doing like 2,000 traces. Do those traces have to be synchronized as well?
Yep, so those traces, this is where the synchronization comes in. So on my system, I start the recording for the testing right when the device, it puts a clock line high that says I am now doing encryption. So it's perfectly synchronized. I know, from that point there is X cycles before the encryption. So they all line up. They do have to line up. If they don't, it won't work. But if they don't, you can also do some trace resynchronization, because in real systems you'll have interrupts and stuff that are screwing you up. And very briefly, you do some sort of auto-correlation. So you correlate one power trace with the next one, and you just say, at this point, other stuff's lining up, like all the, the rest of it. The convenient thing is that there's only very small variations. So for example, the encryption will do a bunch of subroutine calls that are all the same, and then a bunch of stuff that's all the same. At some point, the data differs, so the power is a tiny bit different. So you will still get really good correlation between the two traces, because they're mostly the same, say for some point, and then they line up, and you're as usual. Other questions? So the theoretical limit of the clock speed, the ADC in this is spec to 105 megasamples. You can run it faster. You know, you could overclock it to, I've done 150 megasamples. You can play some games with undersampling that actually works okay. So I don't know how fast of hardware you can go. It depends a lot on what it is. If you're doing like a cell phone that maybe is running at, you know, hundreds of megahertz, and it's doing the AES in software, you can get away with a pretty slow capture because it's not doing something every clock cycle. So you don't necessarily need to measure every single clock cycle on the data. You can average over a bunch. It's really highly dependent on the hardware. But the idea of the synchronized capture also is that worst case you would have to buy a faster ADC, which still isn't super expensive. You know, you can get a gigahertz sample ADC for a few $100s type thing. Other? So the question was, have I done other security? And no, the answer. I've only used AES out of time. All of these principles apply to typically whatever else you want to use. Anything where you effectively can do this operation I talked about, that we know the algorithm, we know the input, and I just need to figure out some point that I can hypothesize what the data is, and then do this correlation between the hypothesis and the point. So this specific algorithm isn't too relevant.
What are your thoughts about attacking the device where the algorithms on that? I worked with a $107 a while back in a flash encryption that was completely undocumented. I'm kind of curious about how one might be able to crack that, get this cracked.
Yeah, so the question would be then, because you can break hardware AES, so for example, it depends if they've tried to make it difficult or not, basically. The example I gave before where someone's broken the XMega, the XMega is a microcontroller that has specifically a hardware AES core, so this paper here. So this has AES done on the physical hardware chip itself, and they were able to break it. So just because it's in hardware doesn't mean it's uncrackable. It may be, for example, smart cards have hardware encryption as well, but they have countermeasures designed specifically to stop this, which isn't to say it's impossible. It's much more difficult now. So it would depend if they did that or not.
Okay, I was more curious about like devices where it's clearly not AES, just some little cap.
Oh yeah, XOR probably.
Yeah.
I mean, anything that you can figure out this intermediate state, you should be able to. Really, the whole thing is about that you can figure out the Hamming weight of data on the bus. What that gives you depends on what you do with it. Other questions? All right, how much time do we have here? 2 minutes? All right, well, we can see if this demo is finished running.
Is it only practical to do that intermediate, like for an unknown algorithm where you only can see input and output? Is there anything, and this is probably a really stupid question again, so I don't know of trying to correlate to the output?
So yeah, you need to know the algorithm, and you need to know one of the states. So you can do this with decryption or with encryption. Doesn't really matter. As long as you need to know one of the inputs or outputs or something, and then you can do this guess where you say, well, if the key guess was right, this would be the intermediate state. So as long as you know the algorithm and the input or output. So I think that's probably time. Yeah, so official time. So I do have 9 PCBs with me, very limited, but if you're the type of person that would actually use them, and only take them if you really, really, really will use them, and promise me that. Yeah, okay, okay, good.
Are they 2-layer, 4-layer?
It's 2-layer, so it's not, as a quick note, you have choices of what you build. You can either build everything if you're really good with soldering. Sections of it is all 402 capacitors and stuff like that. Sections of it is much easier. So there's documentation and DigiKey lists and whatnot. So, all right, thank you for coming, everyone. If you have more questions, come up to me.